Hello, everyone. Welcome back. This is part two of our series training on R. From the first video, I have received some comments suggesting that I could release the content of this training in English so that it can reach a wider audience. So, considering that, starting from this uh, program to the remaining series, the videos will be in English. So I'll try to explain it as simple as possible. Just as a quick disclaimer, I'm not a programmer or a machine learning expert or data scientist, but I'm trying to share the practical aspect of or the practical application of R for health science and biomedical research. From my first video, I have tried to highlight, different types of research methodologies that we mostly apply in the health science and biomedical researches so that we are trying to look into the most suitable statistical approach to address those different types of clinical and biomedical research questions. So having said that, I will directly go to the today's program. Today, we will be covering on the data manipulation, data handling, as well as data clearance. And we have also some missing values, so how to handle those missing values and how to identify the missing values from the different variables using R. As a quick reminder from the first program, we previously used the read CSV. Let me take you there. Just one moment. Yeah. So we used the read CSV function to load our data from the folder. So the next part would be done, and we have seen the data that we have imported here, right? So this is the data that we have already imported, and we can clearly see the types of variables we have and the number of observations recorded in this file. So basically, I have 1,000 entries with a total of 12 variables. So we're going to see how many missing variables existed in each variables or columns so that we can decide what kind of approach we're going to do to treat those missing values. The next step would be to understand the data structure using stir function. Okay, here. We'll say cancer data. This is the file name. So now we can see the data structure. So we have this patient ID. Its data structure is in integer. So you can see here, and the gender, which is a categorical variable, male or female. So this is a character, and the tumor size, stage, and the tumor size, also the integers and the stage and the treatment group. And here, the status and the status. These are the character. The remaining is we have also numerical, like biomedical. So whenever we have this digit, so we can it consider data as a numerical. So once we have seen the structure of the data, and so you can also simply click here and see the structure of the data. So either of the two can work well. So either you can click it or you can use this function to see the data structure. So once we have visually inspect the data that we have imported and understand the structure of the variables of the data, the next thing that I would do is I will try to look into handling missing data. So as I showed you earlier in my raw data, so there are some missing data in some of the variables. So that first I will label like, handling missing data. So how are we going to do that? One is basically in R, the missing values are represented by NA. Usually, I think it's very common in research that NA is not applicable. So it is, if it is NA in the values, so we can look at the raw data. So basically, we have here one missing data and here. So these are the missing data in our original data. So next, what we can do is we can use function combined with the is NA function with the combination of some function to count the number of missing values in each column. So this would allow us the how much of from 1,000 observations or entries, how many of missing data exist in every column or variables. To count the number of missing values is we can do, oh, sorry, it comes by itself. Then this is the function to count the NA. NA is the missing values, and you'll put the file name. So the file name is cancer data 2. Then we press Control plus Enter, or we press the Enter the run function. So here you can clearly see that from each uh, columns, how many missing values existed in this at the bottom. So in the patient ID, there was no any missing value with age, gender, with a tumor size. Out of 1,000 observations, there were 50 missings, and tumor stage no, treatment 30, biomarker A 25. With the remaining, we don't have any other missing values. The next step would be, so there are different ways of handling missing data. One of the simplest ways is to remove the entire row so that this data element will not be incorporated in the analysis. The other way is we can take the mean or the median or the mode of the column. For instance, if it is a quantitative variables like age or for instance, the glucose level, hemoglobin level, we can take the average, the median, or the mode depending on the distribution of the data, and we can replace the NA with that value. That is another alternative. And the other alternative is we can apply imputation to fill the missing values using regression models. First, I need to save. So whenever we have a new version, when we do, for instance, manuscript preparation, we might have different versions, right? So for this particular version that does not include the missing values, we can save it separately. How we do it, that one, we can give a name, for instance, clean cancer data 2. Then we will assign the subsequent data that does not have the missing values will be present with this name, right? So this is how we do the saving separately. That means the original files will not be removed, or it will be retained. So we'll do that one. So NA omit from which file? The file name is cancer data 2. So we are creating a new file named clean cancer data 2 that will not have the missing values. So let's create, we created, and let's see the new data. Clean cancer scans. So we open one. So as you can see clearly here, we can't see any missing values here, just visually. And you can look at the total number of entities reduced from 1,000 to 854. That means 146 values were removed. So all of the rows that has the missing values are removed from this file. So another way to confirm is to run again the column sum, right? So we can look at whether there is any missing values in this file. So we need to replace this cancer data 2 with clean cancer data 2, and we run. Okay, so there is a mistake, clean cancer data 2. Oh, yeah, because this is capital. This is very case sensitive, so we need to bear in mind. So we run, so we can clearly see here from patient ID, age, in all of the variables or columns, we don't have any missing values. So if we are fine with removing these missing values, so for the subsequent experiment, for the subsequent analysis, we'll be utilizing or we'll be calling clean cancer data to sheet. So we're no longer using cancer data 2, which are these missing values, the original data set, right? So this is what to do in this step. So if you assume that uh, removing this missing data affects the reliability of the result, then you can apply. The simplest way of doing it is you can check the mean, median, mode, depending on the distribution of the data, and replace the missing value. That's one of the choice. The other choice is you can predict using regression models based on other variables in the model, then you can replace with that. So I will make another separate video for imputation, which is another, statistical analysis. I don't want to bring it here because this is more of, introductory. So this is, let's assume that this removing missing data would not affect the, the outcome of the result. Now we have a clean data without any missing values. So the next step would be to go into exploring, some of the descriptive analysis that we can do to understand the data we have. So I would label here descriptive analysis. So what do we mean by descriptive analysis? It means analyzing the distribution of the data in terms of mean, median, standard deviation, proportions, the width range, more or less such kinds of analysis. So in order to have a quick overview on the data distribution of each variable, we will run a summary function. So for a summary function, we'll be applying the new file name, clean cancer data and run. So here for each, at the bottom, for each variables and column or columns, you can see the mean, the first quartile, the median, the mean, the minimum here, and the mean, as well as in the third quartile, the maximum. So you cannot have the range, the 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 the, the measurement to understand the central tendency, as well as how much the data is dispersed among themselves. So you can have these all different types of values for quantitative variables. For the qualitative or categorical variables, you only have the lengths, how many lengths or how many observations are there. Then we'll come that with the proportions to understand the distribution of the male, female among these 654 and different types of these mutation statuses later on. So sometimes you might want to calculate the specific statistics to certain variables to find out one. For instance, if you want to only calculate the mean, and if you don't want about the median, the mode, or these quartiles, you can simply say the mean, and then we can say clean cancer 2, and to make specific. So when we run this, so it will calculate the mean of all of the variables. So basically the error is because some of the variables are character or categorical. So it does, so we need to specify. So in order to specify those variables with the quantitative property need to be assigned. So we use the dollar sign. The dollar sign allow us to make specific to the types of variables we want to analyze. So let's say we want to analyze tumor size. Then when we run it, then we have here, it is 13.4 is the mean of this one. If you want to calculate the mean of clean cancer, and you need to, the dollar is to make the selection specific to the variables. Then we go to like biomarker A, then we press run, then it is 99. So by doing that, you can calculate a specific uh, tests for each um, variables. Let's assume that if you don't want to remove the the missing values and you want to keep them, but during analysis, if you want to remove the missing values from the analysis, what you can do, let's say, let's calculate the mean. Let's calculate the mean, and now we will call on the original data, right? Cancer data too. This is with uh, with the missing values. So to calculate this one, what you can do is you can specify and uh, let's calculate the tumor size. Yeah, tumor size. It should work. Okay. You can compare here. It becomes 30.4. Here also 30.4, but if you move further, it is 30.43, 30.41. So there is a minor difference. So that removing this particular would not affect the mean of the values, right? So because the number of observations we have here is 1,000, it's not small. Okay. So similarly, if you want to do the median, you can do it simply. So then clean cancer, it comes. Then we need to specify the column with dollar sign, which one you want, maybe tumor size, then run. So you have 30. So basically by doing so, you can calculate, the mean, the median, standard deviations, the mode, everything, whatever you want, depending on your research question when it comes to the descriptive analysis. Maybe just to show you the standard deviation, because that's one of the common statistical tests. So standard deviation, let's call on the original data with the missing values. Clean, sorry, not clean. Cancer data 2. And we need to specify which variables we want to calculate tumor size. And let's remove NA dot. This is remove is equals to if it is true. That means if it exists there, it will remove it. Without removing, let's calculate if there is a difference. Then clean cancer. Let's specify the it's I think tumor size yes. And since we are using the clean one, we don't need to put this condition. Yeah, so basically here it is 15.08, here 15.07. So more or less the same. So removing that particular data point would not affect the data structure in terms of the distribution as well as the average of the data in that particular variable. Okay. Then next is, so we have seen for the quantitative variables. So this is basically for the tumor size, something that we can measure, right? So for that, we can calculate mean, median, mode, depending on the distribution of the data. So the next part is we want to see the distribution of the categorical variables. For instance, we have gender, how many of them are male, how many of them are female among these 800 something observations, right? So for these variables, what we can use is we can use the function table here. Uh, Then in this table, we can simply call the clean file, clean data. Then we can specifically call gender, right? So we do this one, run. So as you can see here at the bottom, we have female 416 and the male 438. And another alternative is to calculate the proportion. So how we can do that is we can also get the proportions by dividing the table by the number of total observations among this cleaned data. So we do that one. The function is proportion table. Then we open parentheses and we do table. Then again, We open a new one, then we include the clean data, we make it specific to gender, and we run it. So now earlier we have the actual number. Now we have in percentage or in proportions. So now we have seen how to calculate the mean, the average, the proportions, right, from different types of variables, categorical, numerical. And so based on this, we can, you know, create a table and we can feed these values in the table in a publishable way. Then we will come that later on. Now, let's go to the visual aspect, right? So we have seen the descriptive analysis. Let's visualize our data. Let's do that one for the visualization part. So there are various graphs that we can generate using R. So for the numerical data, as a basic uh, graph design, we can generate histograms, which is the most preferred. And it's great to see the distribution of the single numeric values, right? So how the data is distributed, whether it is normally distributed, whether there is a right or left skewness. So this would help us to understand the data distribution. So to doing that, we have a function called histogram paste. Then what we can do, we can directly call the clean data file and specify which variables you want to analyze. Let's analyze tumor size and put comma. Then the next part would be once we have defined which variable that we wanted to analyze, we are writing this main function and then what we want to see is we will give this a title, maybe distribution of, these are patients, right? It's like patient data. So let's say uh, distribution of patient tumor size. Let's say distribution of tumor size in simple. Let's say distribution of tumor size. I think that's more easy, right? Then we can also include additional features that xlab be, that means the x-axis would be what we want. That one is tumor size, tumor size. Okay, so I think we are good. Let's run it. Yeah. So as you can see here, this is a histogram. So we put the x-axis tumor size and the name of okay, I think there is a mistake here. Tumor size. Run again. Yeah, tumor size, right? So this looks like, a good histogram, right? It's a normal distributed. Majority of the tumor sizes are around 20 to 40. So this should be I think, a good distribution. So the next part would be, so now we have seen individual data, right? Individual quantitative data, individual quantitative continuous data. So the next part would be, we want to compare between groups. So for that, let's plot box plot, which is one of my favorite graph for comparing the distribution of numeric values across different categories. So in this regard, let's uh, divide this tumor size between male and female, whether the distribution is more or less comparable or whether there is a difference. So for box plots, we will write box plot. We have this function here. So first, what we want to write is we want to write the variables that we want to compare. So we want to compare tumor size by gender, right? So I think gender is written like this in the table. Then we will make sure where the data is coming from. The data is coming from the clean data type. Then we need to specify that one, and the title of the table would be main, and let's say tumor size by gender. So once we did that one, this needs to be in quotation. Then the next would be once we specify the title, then now we have these two groups, right? So basically we need to have the y-axis and the x-axis. So y-axis is y lab, that is for labeling the y-axis. So I want to say that one tumor size. We need to make it in quotation, and X labeling would be gender. Here, as you can see now, we are comparing the tumor size across different genders. So the box shows that the middle 50% of the data lies here, and the line inside is this is the median, and we have this extended shows the range of the data, and these are the outliers in this data. So the next part that I would like to explore today is scatter plot. So the scatter plot help us to see if there is, any relationship between two numeric values. I mean, numeric variables, like for instance, tumor size with their age, tumor size with their, other quantitative variables that biologically make sense, right? So in order to do that, so what we do, we need to run plot function. So in this plot function, we need to call the name of the data file, clean. Then we need to make it specific in this regard. We want to compare like maybe age, uh, and let's call another one again. We call again clean cancer data. From the same data, we will compare age with, let's say, tumor size. And then once we are sure with that, and now we go to with the label. For the labeling, we used main. So what we want to say here is age by tumor size. Okay. And another thing, so we need to make this one in quotation. Then we need to label the x-axis with, let's do this one age, and the y label with tumor size. Okay, let's run. Okay, what's okay? Tumor size. We need to put this one. Okay, H. So let's run this and see. So this is the tumor size and H. It doesn't seem it has any sort of relations between these two things. Let's check another plot. Let's check another plot. Let's do tumor size, maybe biomarker A. Tumor size. Let's copy paste this one. Actually, yeah, you can copy paste. Okay, then we can replace this one biomarker by tumor size. This will be biomarker. Okay, let's do it. Okay, so no relationship. As I said earlier, so this is not real data. This is just to show you, to demonstrate how you can generate publishable standard figures. So you can clearly see here. So just bear in mind that when you are labeling, we need to put the unit, for instance, how you measured it, right? It might be microgram per ml or nanomolar or whatever the measurement that you have here. Tumor size, it might be centimeter, millimeter, micrometer, in whatever sizes. So for publishing such kinds of data, we need to have appropriate labeling with their unit. It's very clear, right? So we have the scatter plot. We will come to that, what scatter plot means, in what conditions we need to use the scatter plot. So the objective of today's presentation is to show you to how to explore your data in terms of, its data distribution using the common descriptive analytics and visualizations. So having said that, this is it for today. And what we have done is we have seen our data, we cleaned it, we removed the missing data values, and then performed some initial or basic descriptive analysis and visualizations, which are, I believe, very critical for health and biomedical researches. So these are, I mean, it's very foundational, right? So in the future videos, we will build on this foundation and explore more advanced statistical techniques and applications that are very much needed for this kind of research. So thank you for watching, and don't forget to like and subscribe and share these art tutorials, particularly for youngsters working on their research, master students, PhD students. And if you have any comments, suggestions, you're welcome, and see you next time.